So good morning, everyone, and welcome to the very first NDC AI. How are we all feeling today? Are we excited to be here? Yes. I am very excited to be here today, and I'm very excited to be speaking about a topic that is very near and dear to my heart. And that's the topic of whether you can trust your models. So I've worked as a data scientist for many years now, and this is a topic that I have had to tackle many times throughout my career. And it's not an easy question often to answer. And it's even harder now because we've moved into the age of gigantic, complex black box LLMs. But of course, we are talking about data science. We are obviously talking about something much more scientific than the idea of blind trust. We're in fact talking about the question of whether you have measured things properly. And to illustrate the difference between trusting your results and actually measuring them correctly, I'm going to start by telling you a story. So back in 2010, a social psychologist called Amy Cuddy was teaching at Harvard Business School. And she started noticing a difference between her group of students. This is always the problem when you study undergraduate psychology. Your professors start experimenting on you. So she had two types of students in her classes. She had one group that was doing very well at written assessment, but when it came to class participation, they were very reluctant. They would half raise their hands, almost as though they were protecting themselves. And when they were called upon to speak, they were very reluctant. They lacked conviction in what they said. But then she had another group of students. These students were doing very well at written assessment, but they were also very keen to do class participation. So they would raise their hands high, and they would have a huge amount of confidence when they spoke. So Cuddy got to wondering, could there be a relationship between confidence and body language that went both ways? That is, by having more confident body language, could you actually become more confident? So this kicked off Cuddy's research into what she called power posing. And what she did is she got a group of participants and got them to do some sort of difficult, intimidating task. And she divided them into two groups. And one group, she got them to hold these sort of expansive, high power poses, like this one, the Wonder Woman pose. And she found that this group actually were more confident at doing this task. They reported feeling more confident, they reported more feelings of power, but most importantly, they actually showed physiological changes that reflected this. They had higher levels of testosterone and lower levels of cortisol, so they actually were feeling more dominant and less stressed. So these were exciting findings, and these actually really impressed the scientific community. Cuddy ended up with a publication in the top journal in psychology. And then her findings hit the mainstream. She ended up with press interviews. She ended up on Oprah, and she ended up with one of the most watched TED Talks of all time. Remember, this was 2010. So people everywhere were going into bathroom stalls to power pose before, say, job interviews, or holding these poses before doing something difficult like walking on stage to Keynote in front of 400 people. Cuddy and her power posing had become a phenomenon. That was until 2014. Another researcher called Ava Rainhill tried to replicate Cuddy's findings. Replication is one of the cornerstones of science. And she actually wasn't able to replicate most of Cuddy's results. Importantly, she wasn't able to replicate those all-important physiological findings. And other researchers started paying attention to Rainhill's failure to replicate, and they too were also unable to replicate these findings. And this whole unhappy saga came to a head when one of Cuddy's original co-authors on their power posing paper publicly disavowed their findings. And this called Cuddy's credentials as a scientist into question. So what happened here? Was Cuddy a charlatan? Or was she perhaps incompetent? Well, neither of these was actually true. Cuddy was a rigorously trained scientist. She did her PhD at Princeton, and remember, she was doing this research while she was at Harvard. Instead, Cuddy had followed what she thought was the methodological standards of her field, but she'd made a major mistake in how she'd assessed things. So she trusted results that looked real, but they in fact told her the wrong thing. So I know what some of you are thinking. It's psychology. It's not very scientific. And, of course this sort of stuff happens. But this could never happen in machine learning. Machine learning uses all this complex math and all these beefy NVIDIA GPUs to crunch numbers. This could never happen in machine learning. Well, not so fast. In a review of studies across a number of fields that used machine learning as their core methodology, it was found that in every single field, at least some of the studies had such major problems with how they'd measured things that the results were incorrect. So in every field, at least 15% of the sampled studies had these problems. In many fields, it was more than 50%, and I don't know what's going on with satellite imaging, but every single one of their studies had this problem. And you can see this includes fields that are, potentially seen as more objective. Things like genomics, medicine, and, oh yes, software engineering. We didn't escape this. So let's have a look at an example of one of these studies. So what they were trying to do in this study was to see whether 4 different machine learning algorithms would get different results when solving the same problem on the same data set. And you can see that they actually did find this. They found that newer, ostensibly more sophisticated methods outperformed the older and simpler logistic regression. And this kind of intuitively makes sense, right? You might think that something that is a bit more sophisticated could potentially learn more patterns from the data compared to logistic regression, which is known for underfitting. Except none of it was real. The authors had made a major error with how they'd assessed their results. And when this was corrected for, there was no difference between the algorithms. So this raises a rather troubling question. If even experts in machine learning, people who have contributed results to the scientific record, have made such grave errors, how can we be sure that we have made good machine learning models? How can we be sure that we've assessed their results correctly? Well, in order to answer this question, we can borrow from a branch of mathematics called measurement theory. And measurement theory tells us that a robust machine learning model has 2 properties. It's reliable and it's valid. So reliability is essentially that the results that a machine learning model gives you are consistent. And there are a few different aspects to this. The first is that when you put the same inputs into the model, it will give you pretty much the same outputs. And this will be consistent and stable over time. That model, will essentially give you the same outputs for the same inputs in 6 months' time, in 12 months' time. And in addition, similar ways of assessing the same thing will converge. So it might be that you're comparing the results that are given from a machine learning model with those given by human assessors. Now, validity, on the other hand, is measuring what you set out to measure. And this is actually, surprisingly difficult to do. You might think, this sounds really obvious. Why would you not measure what you meant to measure? But you're going to see throughout this talk, this is surprisingly hard to get right. So there are a few different facets of this. Firstly, what you're trying to assess is very well defined and very narrow. In addition, this clicker is having some problems. If you are measuring very similar things, the scores that your models are getting on that should essentially be highly related. In addition, your models should perform as well in the sandbox of your development environment and then perform equally well in the real world. So to start, let's look at a major threat to reliability, and that is data leakage. So I think an intuitive way to understand data leakage is to imagine that you are a professor giving an exam. So basically, in order to assess your students, you help them prepare for this exam by giving them a bunch of past exams. But when it comes to test time, you come up with totally new questions. So in this way, you're sure that what you're assessing is how well they've learned the material. And what you're going to expect is a distribution of test scores that are similar to what you saw in previous years. But let's say you're a little short on time. And so you decide to recycle questions from past years. Now, in this case, the question becomes very muddled about what you're actually measuring. Are you measuring how well they've learned the material in the course, or are you just measuring how well they've memorized questions they've seen before? And if that's the case, what you're going to see is an artificially high distribution of scores. They're going to perform a lot better than they would if they hadn't seen those examples. So it works in the exact same way in machine learning models. And we can see that in the case of a model called ChecksNet. So ChecksNet was designed to automatically detect if a person had pneumonia based on their lung scans. And when they tested this model, it performed extremely well. So it's great, right? We've got this super cool model. Hooray for science. But there was a huge problem with how they'd assess things. What they hadn't realized is that people, when they go in for lung scans, get multiple, almost identical scans in at the same appointment. And what this means is that when these were distributed across the training set and the test set, the algorithm had essentially seen answers that it had trained on in the test data. So you can see it's exactly the same as the students with the exam. You give a machine learning model the answers in the test set that it's seen during training, and you're going to get an overinflated sense of its performance. So let's now talk about validity. In the really early days of machine learning models, when we had more basic models like regression models or decision trees, it was relatively easy to see what the models had learned from their data. So these models are highly explainable, and it's really quite easy to see if something's gone wrong during training, and the model might be learning something different to what you think it has. So we can see that in the case of this linear regression model. This model has been trained to predict students' exam scores. What you can see is a bunch of features. These are the things that are used to predict the scores, and a bunch of weights. This is what the model has learned about those features during training. And if we take, say, this hours spent studying, what the weight signifies is that for every hour students spend studying, they're going to get an extra 1.5% on their exam mark. This is highly explainable. It's easy to understand what the model has learned. But as we've moved further into the era of black box models, models that are not transparent and explainable, we've had to come up with creative ways of trying to work out what the models are learning. So we can see that in the case of this vision model. This is a convolutional neural network. We can pull out the hidden layers, and we can see that it seems to be sequentially building up an image of a cat. But we have to add our own interpretation to that. Or in early, small large language models, which is a very unintuitive term, like BERT, we can actually look at the layers and see what the relationship between the words is. But again, we need to add layers of interpretation to this. And things have gotten really difficult as we've moved into our current era of massive large language models. It's no longer really possible to get a gestalt idea of every single point that is going into the predictions that these models are making, everything that it's sort of learned from the data. There is actually some very interesting work that's coming out about LLM interpretability. If you want to learn more about that, I can only recommend sticking around for my friend Michelle Frost's talk in the next session. But largely the way that we assess LLM performance at the moment is working out, does the output make sense in relation to the input? So we can see that in this example here. I've asked the LLM to write a joke about cats, and it has. We don't know exactly how it knows what a joke is, what a cat is, and how it combines those concepts. And things have really gone off the rails because now we also cannot assess reliability correctly. So it used to be that with machine learning models, although the training process is not deterministic, once the model is trained, predictions pretty much are. For the same inputs, you will get roughly the same outputs. But by design, LLMs don't work this way. You will put in an input and you will get multiple different outputs for an identical input. So this is because of a mechanism called temperature. Basically, in order to make the speech that comes from LLMs sound more natural, we've essentially introduced some randomness in the next word that's predicted. So basically, from the pool of potential next word predictions, one is chosen rather than just the top one. And this is great. It does mean that the models perform in a way that feels a bit more natural, but it does also mean that reliability's gone out the window. So it brings us back to the question I asked earlier. How can we know if our LLM is good? How can we know if we've properly assessed LLM performance? Well, if you've been a person existing in the world for the last couple of years, you will have definitely heard an LLM model provider telling you how great their model is. You've seen some variation of this. We just launched our newest large language model, trained with state-of-the-art GPUs, and we've improved on the MMLU by endpoints, beating the previous best. Or perhaps you've gone a little deeper down the rabbit hole and you've come across LLM leaderboards, which pitch these models against each other on exotic-sounding measures like Winograd or Hellaswag. But what's going on here? What are these benchmarks actually assessing? And does an LLM scoring well on them actually mean that it's good? Welcome to the noisy and confusing world of LLM assessment. So to start this discussion, let's start talking about what I think is one of the most inflammatory ways of assessing LLMs, and that's seeing how well they perform on the hardest exams for humans. So we can see a case of that here. What we have are 4 LLMs, and they've been tasked with completing questions from a US medical entrance exam. And we can see the models have done great. The best performing model got everything correct, and even the worst performing model still got 75%. Now, if you think back, remember we saw results like this everywhere a couple of years ago. People were putting medical school exams, legal exams, leet code puzzles through these models, and they were getting very impressive results. And then, of course, the corresponding claims came. They're going to replace doctors, they're going to replace lawyers, they are going to replace software developers. But it has been about 2 years since we started seeing these claims, and there's been no material progress towards any of this happening. In fact, I would argue the opposite has happened. We've had a few very foolish lawyers try to get LLMs to create case materials for them, and they've been disbarred because the LLMs hallucinated precedents. So what gives? How can these models perform so well on these assessments, but fail to do the jobs that these assessments measure for? Well, if you've come to any of my talks before, you would know that the reason for this is because when we try to apply apply assessments created for humans to LLMs, they're assessing fundamentally different things. So let's first talk about what it means when we give one of these exams to a human. The reason we do this is because we expect it to act as a proxy for their future performance. So we take the case of medical school entry exams. This actually works pretty well, has a pretty good validity. In the performance that a person has on a medical school entrance exam is a pretty good predictor of how well they'll go in medical school. And then how well they go in med school is a pretty good indicator of how successful their career as a doctor is going to be. And the reason this works is because both the taking of exams and the practice of medicine tap into a concept that humans have called G, or general intelligence. This is a type of fluid intelligence which allows us to learn crystallized intelligence skills, things like reasoning, things like the understanding of specific knowledge in medicine. And it also allows us to flexibly apply that crystallized intelligence to a wide variety of things like taking exams or practicing medicine. So what does it mean when an LLM performs well on one of these assessments? Well, it means that the LLM is good at doing the sort of puzzles that are in these exams. Nothing more, nothing less. But why? Why can we not assume that this is also a proxy for intelligence in LLMs? Well, it comes down to how and why we train machine learning models, of which LLMs are a subset. All machine learning models are trained with a specific training goal in mind, trained for a specific purpose to do a specific task. In the case of ChexNet, this was being able to predict whether people had pneumonia from their lung scans. In the case of LLMs, specifically GPT models, this is predicting the next word in a sentence. Now, the training of models is very cumbersome. In the case of supervised or semi-supervised models, which GPTs fall under, what you need to do is take some sort of observation in your training data set. You then pass it into the model and get the model to make a prediction. The model compares that prediction against the correct answer, and then it slightly adjusts the model weights in order to be able to try to get a little bit closer to the correct answer the next time. Now, this is a very, very time-consuming process. And as such, the creators of such models have optimized them to get to training goals as quickly as possible through mechanisms like gradient descent. And arguably, it's very, very difficult to see that models would just veer off and develop something as complex as general intelligence, which is really not needed for the prediction of next words as part of this training process. So, benchmarks for humans are no good. But what about the benchmarks specifically designed for LLMs? Well, we saw this humble-looking table a few slides ago. So this is the Hugging Face Open LLM leaderboard. And up until the middle of last year, this version of the leaderboard was considered one of the key ways of assessing whether LLMs are good. And what it does is basically open source LLMs are submitted. They run against a series of gold standard benchmarks. All of the scores are collated, and this collation is used to rank each of the models. But up until June of last year, this was the case. And then this leaderboard was retired and a new one was created. But why is this the case? If it was so trusted, why was it then not trusted and discontinued? Well, there are a few reasons for this, but the reason that I personally find the most funny is because many of these gold standard benchmarks were in fact not quite the gold standard they'd been held up as. So many of these items had typos, they had incorrect answers, they had straight up nonsense in them. So we're going to see a few examples of these. And we're going to start with the MMLU. Now, the MMLU in its heyday was such a trusted measure of LLM performance that model providers would measure their MMLU performance down to a couple of decimal places. So it seems pretty scientific, right? Like a couple of decimal places. Maybe not. Let's have a look at one of the items. And before I show this to you, I need to make it clear, this is the complete question. I haven't left anything out. The complexity of the theory. This isn't really a question. This is, in fact, a sentence fragment, but maybe there's more of a clue in the answer key. 1, 2, 3, 4, 1, 3, 4, 1, 2, 3, 1, 2, 4. Now, keep in mind the idea of these benchmarks is to compare how well LLMs score on them against humans. I don't know about you, but I have no idea why the correct answer is C. All right, next one. This is from one of my favorite measurements because it's so bad, called the HeliSwag. This also used to be a benchmark measure. And before I show you this question, I want to defend myself by saying I have typed this out exactly as it appears in the benchmark. Men are standing in a large green field playing lacrosse. People is around the field watching the game. Men are holding t-shirts watching into lacrosse playing. Are being interviewed in a podium in front of a large group, and a gymnast is holding a microphone for the announcers. Are running side to side of the field playing lacrosse trying to score, are in a field running around playing lacrosse. Now this is garbage. This is a terrible question. But, bizarre imagery and typos aside, I'm guessing we're supposed to answer that there are men playing lacrosse, but C and D both say this, so what is the correct answer? All right, last one. And we could be here for the rest of this talk just going through bad benchmark questions, but we've got other things to cover. So this is from another popular assessment called Common Sense QA. And we're actually off to a good start this time. The question actually makes sense. So when a person is breathing in a paper bag, what are they trying to do? But just hold on, let's look at the answers. Warm air, continue to live, going to sleep, hyperventilation, stay alive. Now, the grammar issues aside, none of these are the correct answer. You're trying to calm down when you breathe into a paper bag. So obviously, after this and other issues were discovered, these benchmarks had to go, and better curated, more accurate benchmarks were brought in. But where does that leave us? Does scoring well on these benchmarks mean that an LLM is good? Well, I hope at this part of the talk, you realize I'm going to tell you not really. And one of the problems that we have with any benchmark measure is actually the answer formats. So when you're creating a benchmark for LLMs, you can get them to answer your questions in two ways. You can, like with humans, provide them with multiple choice options. So we could say, give an LLM a question, what is the capital of Norway? Paris, Stockholm, Oslo, or Berlin? And if it answers C or Oslo or some combination thereof, this would be correct. Or we can get it to generate an answer without reference to an answer key. So if we would ask, what is the capital of Norway? And it tells us the capital of Norway is Oslo or something similar, this would also be correct. Now, what you might have noticed is that so far, all of the benchmarks I've shown you use a multiple choice answer key. And the reason for that is it is quite difficult to assess a non-standardized generated answer, the free-form answers, in an automatic fashion. It often requires human assessment, whereas it's a little bit easier to automate the process of picking from a list of answers. So what's the problem then? We just use multiple choice for everything, right? And problem solved. Well, not really. The problem is that the format of the answer given to the LLM appears to influence their performance. So we can see the case here where we have 3 LLMs and they were tasked with answering the same questions from the same benchmarks. So here's their performance when the answer format was multiple choice. And here's their performance when the answer format was free-form answers. Now, the troubling thing you can see immediately is that for 2 of the models, their performance was worse when they had to answer it as a free-form format. But what is actually much worse and is not reflected in this graph is that the LLMs were not getting the same items correct between the 2 answer formats. This is a validity issue. The 2 answer formats must be assessing different things. And the researchers of this paper speculate that it's probably likely that LLMs can rely more on pattern matching and rote memorization for multiple choice, whereas they have to use the equivalent of more logic or creativity to come up with correct free-form answers. And then there's the problem that related assessments, things that are measuring very similar things, don't seem to correlate with benchmarks that are assessing that same thing. Again, this is a validity issue. As a sanity check, your benchmark should correlate with something that's measuring something very similar. So we can see that in the case of this simple logic puzzle. Alice has 3 brothers and she also has 6 sisters. How many sisters does Alice's brother have? Now, you're developers, I know you like puzzles, so I'm going to give you a moment to solve this and just shout out the answer. 7, correct. So in order to work through this and show you how to solve it, we assume that Alice is a woman's name, so she's one of the possible sisters. Then there are 6 additional sisters. So if we add 1 plus 6, we get 7 possible sisters for each of the brothers. So this is part of a suite of puzzles that the authors call Alice in Wonderland. And they're all a very similar level of difficulty. They're sort of, just basic reasoning puzzles. So what the authors did is they got a bunch of then state-of-the-art LLMs, and they got them to complete all of the Alice in Wonderland puzzles. And then they got the same LLMs, and they got them to complete the reasoning items from the MMLU. So what we have are two benchmarks that are assessing something similar: simple reasoning and more complex reasoning. So what you're going to expect is those scores should be highly correlated. They should lie close to this dotted line. But instead, the authors found a pattern like this. What the hell's going on here? Well, what this shows is that every single one of the LLMs scored much higher on the supposedly more difficult MMLU than they did on the simpler Alice in Wonderland items. And what's even worse is that the majority of the LLMs got 50% or more of the MMLU items correct, but less than 5% of the Alice in Wonderland puzzles correct. Now, this raises a really troubling question. Is the MMLU reasoning items actually assessing what they say they're assessing? And even worse, have the reasoning abilities of LLMs been overstated? Because they can't even complete 5% of these simple puzzles. But here's the thing. These are language models. Should we even be getting them to do things like reasoning or something outside of the language domain? Let's come back to what we talked about with machine learning models at the beginning of this talk. Machine learning models are trained to do something very specific in a narrow domain. So let's say we've got an image classification model. It's trained just to distinguish between pictures of animals. And in the beginning, the domain of LLMs was also similarly narrow. The original transformer models were created for machine translation, and it was soon discovered that they are natural language generalists. So again, the domain was still specific natural language tasks. And so at the beginning, what we had was a suite of language assessments, things like question answering or summarization assessments. And they weren't perfect. It is difficult to do assessment in natural language, but they were at least focused and domain specific and relevant to what the LLM had been explicitly trained to do. But as the capabilities of LLMs have grown, or should I say they appear to have grown, we have created more and more exotic benchmarks to assess these capabilities. Things like seeing if they can do deep problem solving, seeing if they have really specialized knowledge in technical areas, seeing even if they're showing signs of artificial general intelligence. Now, this points to a really huge problem that we've now run into with using benchmarks. If you, as a developer, as an ML engineer, as an AI engineer, you want to use an LLM, it's generally going to be for some very specific purpose. So how does it help you to know that an LLM is really good at answering questions about history, or that it maybe can solve something that looks like, block puzzles? Is this actually relevant to the problem domain you're trying to use it for? This is a validity issue. We've now made the definition of what we assess LLMs on so broad that it becomes very difficult to understand the relevance of those numbers to your problem. So is there an alternative to benchmarks that is designed specifically for LLMs? Well, yes, there is. There is something called the LM Arena. So the LM Arena was created in 2023, and it's a wide-scale experiment. What it is it's set up as a website, and anyone can go there and enter a prompt. And I've entered one: please write me a poem about sausages. And so what the LM Arena then does is goes away and it will pick two state-of-the-art LLMs and it will give you the outputs. And your job is to ultimately decide which one of these you like better. So in my case, I am quite partial to this first poem. Sizzle starts like rain on tin, pepper frets, the fats begin. So the results of my participation in this experiment and everyone else that's visited this website are then collated in an ELO score, like the one used to rank chess players. And this, of course, gives us another ranking and another leaderboard. Now, for quite a long time, the LM Arena, previously called the Chatbot Arena, was seen as the most trustworthy way of assessing LLMs. There was this very famous tweet that circulated by Andrej Karpathy back at the end of 2023. Andrej Karpathy, if you haven't heard of him, was one of the original co-founders of the OpenAI research group. Very well respected person in AI and in natural language processing. But basically, at that point, he really had a lot of faith in the chatbot arena to the point that this was one of the only ways he trusted to assess LLMs. But as time has gone on, kind of pretty much in the last year or so, cracks have started to show with the LM arena as well. And that's because a number of findings have called into question how stable and trustworthy the rankings are. So one of the problems comes down to the intentionality of people doing the experiment. So the creators of this experiment have made an assumption that everyone visiting this website is participating fully and with good faith. So they're fully engaged, they will carefully evaluate the results of each model, and they will give an accurate feedback as to which one they like better. But you can see, it's really easy to just visit this website. I'm sure quite a few of you will visit it after this talk. And, maybe you're just exploring, maybe you're not particularly invested. And it's hard to evaluate the output of LLMs. Sometimes they just blather on. So maybe you don't care, you just randomly pick a model and then you peace out. Or it could be that you are actually a bad actor. So the creators of certain models may go to the arena, look out for tells that indicate that, yes, this output is from their model, and aggressively upvote it. So the researchers of this paper found that having just 10% of participants in the LM arena be either apathetic or adversarial could massively skew the results. It could actually change the rankings of models by up to 5 places. But even if we could 100% trust the outputs of the LM arena, the problem is that the way the LM arena assesses results doesn't really have a lot of validity. You might have noticed that the words that they use to assess models are things like good and bad. But what does good mean? Does good mean that it's more beautiful, more correct, more concise, more verbose, more funny? Does my sausage poem, being good, mean the same thing as a resignation letter to your boss or a speech you write as the best man for someone's wedding? Please don't use LLMs to write your best man speeches. Please just write them from the heart. But you can't compare these things. And that's because we now try to apply LLMs to so many different use cases that it's become extremely difficult to come up with one concise way of assessing all of them. So it forces the creators of things like the LM arena to use terms that are so vague, they're essentially meaningless. And this means that the LM arena has gone from being one of the most trusted ways to assess LLMs to now being called a vibes-based assessment. So we talked a lot about validity. So let's now circle back to reliability. We're going to come back to our old friend, data leakage. Now, data leakage is a massive threat to the correct assessment of LLMs. And this is because LLMs are trained on absolutely enormous data sets, which are scraped from the public internet. What this means is that you, as a user, if you're trying to do some sort of informal assessment, you may source something, say like a coding puzzle, to test out the LLM, and you can't be sure if you're actually testing its true ability to solve that puzzle, or you're just showing it something it's already seen. And to sort of complicate this problem, pretty much for the last 2 years, even the creators of open source models no longer make their data sets publicly available. So even if you had a way of looking through that data set for your coding puzzle, you can't even access them anymore. So there's a really nice example that shows this very clearly. So going back to the release of GPT-4, we had all these people saying, we're going to be replaced by LLMs. And a researcher called Horace He, who's one of the people who contributes to PyTorch, he basically was like, this doesn't seem right. I smell data leakage. So what he did is he went and got some puzzles from a website called Code Forces. These are coding puzzles, and what makes them great for this experiment is that they're timestamped. When they were released is clearly marked. So he got a group of puzzles that were available at the time that GPT-4 was trained and could have ostensibly been in the training data. He passed them through the model and it got all of them right. But then what he did is he got another set of puzzles, and these ones were released after GPT-4 was trained. So the model could not have had them in the training data. And this time, even though the puzzles were of an equivalent difficulty to the first set, it got every single one of them wrong. So to confirm this was data leakage, another researcher, Sayesh Kapoor, he explicitly asked GPT-4, come on, about a Codeforces puzzle that should have been available at the time it was trained. And indeed, GPT-4 confirmed that this model was in the training data. So these problems with data leakage go deep. And they're so deep, they've actually affected the benchmarks. A review of popular benchmarks showed that dozens of them had at least partially leaked into the training data for the ChatGPT models. And you can see that 75 question answering benchmarks alone had at least some leakage into these models. And you can see this affects all of the major ways that we use to assess LLMs, things like natural language inference, natural language generation, math, and programming. And the problems with data leakage are complicated by the fact that data of sufficient quality to train and assess LLMs is a finite resource. We're actually approaching the point where we may run out of it. So some of the wisdom behind training more and more powerful LLMs is scaling. This is the idea that you feed more and more data into these models. And you can see how this has gone over the past 5 years. We've gone from 500 billion tokens used to train GPT-3 back in 2020 to an eye-watering 36 trillion to train Qwen 3 this year. But the problem is that the amount of publicly available data that's of sufficient quality to train these models tops out at around 300 trillion tokens. So estimates are that we're going to run out in less than a decade and potentially by 2027 if we keep training aggressively. Now, this is data leakage on a scale I've never seen before in machine learning. If every piece of publicly available data of sufficient quality to assess these models has been consumed by them, how are we going to assess them anymore? Now, of course, the creators of the newest generation of benchmarks keep them private so that they can't accidentally leak into the training data. But that doesn't help us necessarily with lay assessments. If we're just playing around with the latest model, we use something from the internet, we may inadvertently be testing it on something that it's already trained on. And this is, of course, accidental contamination. There's also evidence that the creators of models are deliberately gaming assessments by tuning their models to benchmarks in order to get artificially high performance. So a rather notable case of this happened in the middle of this year with the LM Arena. So what the LM Arena does is if you want to release your model onto the website, you are first given a private testing set. So what this private testing set, is intended to be used for is that you will basically take the model you wanted to release, test it once, and then you're going to get an idea of how it's going to perform. But some model providers have been a little bit naughty, and Meta tested 27 variants of Llama 4 against this data set before release. They basically tuned and tweaked and found the one that was going to perform best. So they could basically inflate the performance they'd get on the Arena before the model was released. Now, this is dirty behavior, and it really adds to the myriad of problems we already have that data leakage has caused, and this deliberate manipulation further undermines the few benchmarks we have for assessing LLMs. So to end our discussion of reliability, I want to talk about prompting. But I'm not going to be talking about the cool new area of context engineering. I'm instead going to be talking about something significantly more depressing, and that's called prompt sensitivity. So let's say we want to use an LLM for a text classification task. So we can create a template that looks like this. We just pop the passage of text in the top and all the possible options in the bottom. Or we could format our template like any of these. So can anyone spot the differences between these templates? Just shout them out as you see them. They're not trick questions, they're really subtle differences. Mm-hmm. Yep. And also some punctuation changes. So very, very minor syntactic differences, right? So we have not made any semantic changes. There's no difference in the meaning of these templates. So this should not affect the performance of our LLM at all, right? Well, let's see. So this line here represents the performance of the LLM at this task. 0 means that it basically got no answers right, and 1 means that it got everything right. And these supposedly minor syntactic differences between the templates resulted in an eye-watering 77% difference between the best and worst performing template. This is insane. If I created a machine learning model that was so unreliable based on essentially equivalent inputs, I'd be fired. But this is very much part of the fabric of LLMs. Just to hammer the point home, this is a bunch of models that were state-of-the-art around a year and a half ago, and you can see that when they were tested in a similar way, with semantically equivalent but syntactically different prompt templates, they showed between a 30 to 50% difference in performance. And what makes this even more worrying is that there is no universal template to get the best performance out of all LLMs. It's idiosyncratic to each LLM. So what this means is if we as end users don't know what this is, the numbers we see reported by the model providers are going to be probably substantially higher than what we're able to achieve in our own applications. So this is the point of all of my talks where everyone feels a bit depressed because they're like, why bother? Why bother using LLMs? We can't even trust their performance, so can we use them at all? Well, yes, of course we can. These are very useful models, but unfortunately there are no shortcuts with the assessment. We can't use something, as easy as benchmarks. We can't use something as sexy as leaderboards. Instead, we have to go back to our bread and butter and assess them in ways that we have been assessing machine learning and software development applications for decades now. So to end this talk, I want to tell a story from a blog post by a guy called Hamel Hussain. So he's an ML engineer, and he was tasked with creating a LM assistant for real estate agents, basically a chatbot to help them answer questions. So when he and his team were building this chatbot, what they did was they got a state-of-the-art LLM and they created like a prompt template to handle the most, obvious use cases. And then the use cases grew, so they added those to the prompt template, and then more and more edge cases came up. And the prompt template got out of control, and they had no way of assessing other than vibes. It looks good. And they realized they had a mess. So what he and his team did was they scrapped everything and they started again. And they started building a robust assessment framework from the ground up. And the first thing they introduced were unit tests. And the next thing they started doing was logging traces. Now this looks familiar, right? It looks a lot more like traditional software development and a lot less like esoteric machine learning magic. And then they started introducing humans into the loop. And then from that point onwards, they were basically able to start making bigger changes, start tweaking the models and tweaking the prompts. And they built this all into a rapid and virtual cycle of iteration. So I just want to go through briefly the different levels of assessment that Hussain recommends using. And the first are unit tests. Now, obviously, like many applications, LLMs have many different potential workflows. And you can create unit tests for many of them. So in the case of their real estate application, what they might have is someone asking for a phone number. So what the intended behavior of the application is is that that prompt will go to the LLM. It'll generate a query for a CRM. And the CRM should just return a phone number. So you can write a unit test just to check that it returns one thing. You could make it more refined. You could make it sure that the array being returned has a particular format, just like with regular unit tests. Now, part of the trickiness, though, of assessing LLMs is it's a little more open-ended. What your customers can use your LLM for is a little more flexible. So you can also use LLMs to help you generate more test cases. I'm not saying use the LLM to generate the unit tests, although you can get some coding assistant, but you should be doing the thinking and the work yourself. But you can get the LLM to suggest possible ways that your customers might be using your application based on its intended use, and come up with example prompts and even example data. And obviously, these are high validity ways of assessing LLMs because they're narrow. They're very focused on a specific question you're trying to answer. Now, next, he recommends getting a human in the loop. And he recommends taking your traces, which in the case of LLMs are the multi-step interactions that the LLM has with both the end user and the rest of the system, and getting human evaluators to see how successful the LLM was at carrying out the intended task. Now, how much of this you need to do is not an exact science. You do need to get a representative sample of what you intend your application to be able to do. But once you get enough of this data, you can get another LLM involved in a process called LLM as a judge, and you can see whether that LLM can give you assessments that converge with your human gold standard. And this is a high reliability assessment because essentially you're seeing whether two ways of assessing the same thing give you the same answer. This means you can set up this now in an automated way. You will need to check from time to time that it's still converging on your human assessments. So you will need to, periodically check for drift, but this is a solid way of automating this. And then finally, of course, as with any application, we can use A/B tests. So once we've got everything up and running, we can start tweaking different parameters. So we can see whether potentially we can change the original LLM we're using to be more suitable for our application. Maybe we could even see we can use something smaller that's going to be cheaper to run. We can play around with the prompts that we used, see whether our system prompts can be changed in such a way to give more precise outputs. And of course, we can potentially look into fine-tuning our LLM, using potentially that data we used when we were evaluating the traces. And of course, this is a high validity approach because we have our actual end users giving us feedback on how much they like the changes we're making. So, can you trust your LLM? Yes, but unfortunately, there are no shortcuts to getting to this answer. How much you can trust an LLM should not be based on feedback from model providers or external benchmarks. It needs to come from the use case that you want to use the LLM for, based on hard work, the hard work we've been doing for years now, to build domain-specific assessments and continuously monitoring and updating them. But trying to take shortcuts with the assessments of LLMs, I feel like we've really gotten ourselves into a mess. And I feel that there is a huge gap, a gap that I've never seen with any other type of machine learning model between reality and the fantasy created around these benchmarks. Fantasies that have really perpetuated the mythology of LLMs as a lot more than what they are, a lot more than just machine learning models. Thank you very much. If you go to this QR code, it will take you to a repo that has all the resources I used and the slides. I'd love to keep in touch. Here are my socials, and I'll be here till around 1 or 2 o'clock. Thank you very much. You're a wonderful audience.